introduction. I'm Emma, like Nat Moat. I'm also from Semgrep, so I think this is actually kind of the prequel talk to his talk. And I'm just going to be telling some stories of some silly mistakes we made in our Python OCaml codebase. So quick reminder about Semgrep. So Semgrep refers to two things, actually. There's the company, where we build an AppSec platform centered around what we call secure guardrails. But there's also the CLI tool, which is a security-focused static analysis tool that what it really does is just allow users to write rules to search for bad code. And in this talk, I will generally use Semgrep to refer to the tool, which is what's of interest here. So as an example, and maybe this really showcases the problem because I did write the example using Python, and I realized too late that I should have used OCaml, which we do support. But as an example, you can write a rule using this syntax that says, okay, I'm looking for like $x.write. Like we're looking, let's say like this is an example for like a file, right? And what I'm looking for is for it to be inside this other pattern, which is $x.close and then everything after. And so this will highlight when you close a file and then afterwards write to it. So I did not actually test this rule on target, so apologies if it doesn't quite work, but this will hopefully help illustrate how the syntax looks. So today, we are really committed to implementing Semgrep in OCaml. We're always looking for more OCaml engineers, but that wasn't always the case. We introduced OCaml into the code base. Specifically, it was Yohan Padillo who did it. He pulled from a tool that he had worked on, Puff, at Facebook to do static analysis. And when he brought it, he originally called it Semgrep. That code was already in OCaml, and so obviously he was going to keep developing it in OCaml. But the founders still wanted the company to be a Python company, for many of the reasons that I think we've heard a little and maybe rebutted a little, but just there's a bigger developer pool, there's a bigger ecosystem. So they came to this compromise. The main code was still started in Python. And the founders who were more comfortable with Python built this like YAML-based syntax to combine patterns. But each pattern, because we already had that pattern matching engine in OCaml, each pattern was sent off separately to OCaml. And then in OCaml, we would do the actual search using the patterns for the code, and then like those ranges would get combined back into an actual result. So we ran into a number of problems with this interface. I'll talk about 3 of them. First one was a very simple one. So as you might be aware, functional programming uses a lot of stack. And actually back in these days, the stack overflows would manifest as seg faults, which was very annoying. And so to solve this, we would ask users to raise their limit using like ulimit. So what happened when we actually asked them to do this? Well, unfortunately, even though they had raised ulimit, they had only raised it for the Python process and not the OCaml processes. And so we would just get the same stack overflow seg fault, which was pretty confusing to debug at first. Anyway, that wasn't too bad. So the second problem relates to startup time. And to explain this, I'll need to give some more context about our code base. So the main code we had was Semgrep, which was this Python thing that was calling into OCaml. But we actually had another layer, Semgrep action, which orchestrated how Semgrep worked in CI environments. So like when you wanted to use Semgrep in CI, you would actually install Semgrep action, and it would do some processing before calling Semgrep. One of those things that it would do is, and I don't remember all the details of why we did this, probably just some choice that was easier at the time, but the Semgrep action would collect the files that we needed to scan. And while Semgrep could do some file targeting, like it wasn't what users were looking for in CI, and so we just had Semgrep action call Semgrep with all the targets that it should run on, all the files that it should run on. Some of you guys might see the problem with this. When you have, a lot of people have monorepos, and when you have a lot of files and you have to list all of them, generally, so the Semgrep, the command that you're calling, it can only take up one page. So I think 4096 bytes. And very quickly, you can have more files than fit on one page. And so we would have to break this up into separate commands, one for each page of file names. And this actually could get to be quite a few files. And remember that the Semgrep calls are still themselves splitting up into different calls for each pattern, and that would happen across each rules. And the nuance here is that running the OCaml binary has a startup cost. It's not that big, especially if you run it repeatedly, it'll get warmer, and so it won't take quite as fast. But if we look at how this would play out on an example code base, it wouldn't be uncommon for us to end up with 20 calls from Semgrep action to Semgrep, because it would take 20 pages to list all of the files, listing think about how long file paths can get. And then Semgrep to OCaml, we might have, if you had 25 rules and each of those rules had 4 patterns, that would be 100 calls to the OCaml binary. And so each time, the startup cost wasn't that bad. I think what would happen is, after the future calls, it would only be 0.1 seconds. But 0.1 seconds multiplied all the way up turned out to be a lot of time, especially given that the actual matching was really, really fast. All you're doing is you're taking some code, parsing it, and then doing a match to the AST tree. OCaml is a fast language. This just did not take that much time. And so it happened that the majority of the time we were spending was on startup cost of running OCaml. So I think we had one code base where it used to be timing out after 2 hours. After we fixed this, it succeeded in 20 minutes. All the rest of that time was just OCaml startup time. So yes, as this says, we solved this by just rewriting it. We deleted Semgrep action. That wasn't too bad because most of the code could just be brought completely, just copied into Semgrep. And then the part where we had to rewrite from Python to OCaml was we had to send we sent all the rules directly to Semgrep. This means that now, for one call of Semgrep, you only invoke the startup cost of OCaml one time, and then you do all of your processing, which you have to do a decent amount of processing. But fortunately, it's actually very fast to analyze code in this way. And one nuance was it was hard to replicate all of the file targeting that was done in Python exactly in OCaml, because just maintaining backwards compatibility there is annoying. And so to preserve behavior, we sent down a list of rules and which files that they should be run with. And this way we didn't have to rewrite everything, but we were able to simplify this much more and remove that startup cost. And also, once we sent all the rules to OCaml, we could do some optimizations with them. And those optimizations turned out to also be incredibly useful. So this was all great. But we ran into another problem after this. So the problem we encountered was we were running out of memory. As we mentioned, Semgrep is a fairly memory-intensive process. At this point, we didn't use quite as much memory. This was when we were just doing analysis on one file at a time, where now we analyze across files, which takes much more memory. But even at this point, we would find that large repositories were failing with out-of-memory errors. We had a customer, I remember, that was unable to onboard dozens of repositories. And there was a question we were asking, which was, why does memory use even scale so dramatically with repo size? At this point, like I said, Semgrep only processed one file at a time. So once a file is processed, you should be able to lose all the memory associated with it, except like, okay, yes, the findings will accumulate, but you don't have that many findings that this is going to cause it to scale so much with the repo size. And I think there was another hypothesis that maybe the largest file was larger on these bigger repos, but that also didn't quite feel right. So let's look a little more closely at this targets file I mentioned from previously. So like I said, what we would do is we would say, let's list out all of the files that we want to scan, and then for each file, let's say which rules should scan it. We had to do this. We couldn't just do this by language, because you can ignore specific file patterns in your rules. And so you could have it that like most of your Python files are just running with the same rules, Python rule 1, Python rule 2. But then like one of the files is ignored for one of the rules. And so it's not going to, it's running only like the Python 2 rule. And then OCaml, so we would pass this to the OCaml command, and then OCaml would take it and it would parse it into, let's call it T mappings. We actually call it target mappings, but this is a little shorter for the slides. And then it would do all of the searching to match all the rules against all of the files. Now, once again, people have some pretty big repositories. And so let's do a little bit of math. Let's say you have a repository that's 40K files, and each file is analyzed by around 100 rules. And your file paths are maybe 80 bytes, because you have these, they get really long. And the rule names are also, they're nice descriptive rule names that help categorize them. And so the rule names themselves are 40 bytes. This structure was roughly like, we would get 200 megabyte ones. We would see some that were like 300 megabytes. So that's actually pretty substantial. And then on top of that, remember that we like to use parallelism to speed things up. It's a really great way to make your process faster. But what would happen is we would take this structure, T mappings, OCaml would parse that, and it would hold that in memory, and then we would fork. And if you remember from that Moats presentation, once we forked, initially, each process, it follows copy on write. So initially, you're not using more memory. And so for fast scans, memory wouldn't go up at all. This is part of why we didn't realize this initially. But if you run something for longer, once the garbage collect starts to mark the memory, that's a write. And so copy on write will helpfully take your page and copy it into the memory of the forked process. And so this one 200 megabyte file would become copied into one for each process. And we'd frequently run with, I think -J 11 or 12 was our default. So imagine this 200 megabyte thing suddenly multiplied by 12. And this is actually, there's a subtlety. It's actually worse than this, because when we read in the file, we would allocate a buffer. And that buffer would be up to 2 times the amount of the size of the actual structure following the efficient file reading rules. And that buffer wouldn't always get properly garbage collected before we forked. So there was actually a ×3 cost in here sometimes. So it all added up pretty quickly. So how do we solve this? This problem was definitely trickier. So there were 3 levels of solutions. The easiest one was to simply optimize the target mapping structure. You might have noticed that you don't need to include all of the 40 megabytes, or the 40 bytes of rule names, because each rule is always going to be the same. So what we can do is condense that to just a number, an index for the rule. And that compressed the structure significantly, and that helped for a bit. A harder one was we could just, the targets file was creating a disproportionate memory use. Like at this point, nothing else was using as much memory. And so by rewriting file targeting to OCaml, we could finally eliminate the targets file. And so we weren't allocating this block of memory at the start. But of course, like allocating memory up front is sometimes just needed. And as we moved to interfile analysis, we had to allocate more memory. And so the hardest solution that really finally like solved this problem was for us to use shared memory parallelism. So that was the talk from earlier, and this was one of the major drivers of why we needed to do that. Oh, so this was a pretty short talk. I think some takeaways. I wish we had just written it all in OCaml in the first place. That would have been much nicer. But obviously, that sometimes isn't possible. And so I think what I've really learned is I think that the way we introduced OCaml into the code base was ultimately really effective. Like, we couldn't have said we want everything to be in OCaml. There were a lot of cultural reasons why other people were resistant. They weren't convinced. And this seemed like a nice compromise where OCaml could be used for the things OCaml was good at, and Python could be used for the things Python was good at. And yeah, I think that was a very, what ended up happening is that the OCaml has kept growing and growing and growing because one of the things OCaml is good at is being faster than Python. And so a fair amount of speed improvements can happen by simply rewriting the code in OCaml. Also, I think what the thin interface between Python and OCaml for like our application proved pretty cumbersome. So we got a lot of benefits by moving code to OCaml. And so through that process, this company is fully like, we certainly use OCaml. And so I think what I would do if I could go back is to be more thoughtful about the interface between Python and OCaml, to notice what amount of data is being passed and what that looks like, and to recognize and what the cost of calling the binary is. Because what I recognize now is that that interface is useful, but it does certainly come with a cost. And then also a general takeaway is to always profile end-to-end. I'm obsessed with profiling because I think early on at Semgrep, I ran into so many of these issues that were completely not what we expected to be slow. But the good thing about encountering something where it's not what you expect to be slow is it's usually low-hanging fruit to optimize away, and so that's nice. Anyway, so that's it. If this talk did not completely scare you away from what our code base looks like, we are hiring OCaml engineers, so please hit me up. But otherwise, thank you to the organizers. Let me know if you have any questions.
Great. Oh, sorry. Thank you so much for an amazing talk about OCaml and Python, and how our chat mentioned that should be just rewritten Python in OCaml and there would be no problem. So do you have any questions?
So one of your takeaways was to always profile end to end. How do you do that?
That's a really great question. So we use a couple of profilers. So, okay, so for this one, I think the strategy was, because you can't just profile the binary of this system. So what we did was, like, in the top level call, we kind of had a breakdown of like, okay, these are the vague stages of the program. Like, this is the part that, like, gathers the files. Like, this is everything before OCaml, we call the OCaml binary. And like really, especially focusing on, okay, how long does the actual OCaml binary call take? How much does the Semgrep part take? And that was how we discovered, like, that there was a discrepancy where the OCaml code wasn't taking that long, but then somehow there was this extra time, and then we started to look into where that time could come from. So getting the big picture and then zooming in. In terms of how to zoom in, I've used a few tools that I found helpful. One was landmarks. That was my go-to until we switched to M1 computers. Unfortunately, they don't support ARM. If anyone's listening who supports that, I would love that. We also have our own internal poor man's profiler where we can annotate functions and get the times. And increasingly, we've switched to instrumenting our code through open telemetry using C-Cube's library. So Austin, my coworker, is actually giving a workshop tomorrow in how to do that.
Okay. Any other questions? No more. Okay.
Your talk's a lot of fun. Where was the pressure for solving your performance problems coming from? Was it coming from outside the company, inside the company? And was OCaml or the multi-language setup being blamed?
Oh, that's a good question. The pressure was definitely coming from customers. We had most of our customers were running in CI environments where some of them had, there's a 6-hour time limit by default, but then many customers would have even shorter time limits than that. Similarly with memory, because CI runners only have so much memory. That's why we care so much about it. So yeah, pressure was coming from customers where their goal was everything should scan, and of course, the faster it scans, the better. Was the combination being blamed? I wouldn't say the combination was being blamed. I think people were just saying, let's figure out why this is slow. I think the thing that's interesting about the combination of languages is people didn't immediately blame it. The default was to assume that this was slow because matching was slow, because parsing might have been slow, to assume that the things that are supposed to take a lot of work, we're taking a lot of work. And so we started off by saying okay, let's come up with scenarios where this can be really slow. There are some pathological patterns, and we would look into how to cache them and things like that. And those were all useful investigations. But what it turned out was, for our actual customers, for the performance problems we were encountering, that wasn't the problem at all. The problem was the startup cost overhead or some other thing, rather than the intensive actual work that went into searching code.
Thanks. Okay. Anything else?
Thank you for the great talk. Could you please, out of curiosity, talk a little bit more about the kind of static analysis you are doing, about the patterns you are watching for, and more about the sort of business topic, business theme of your work?
Yeah, sure, I'm happy to. So like I said, Semgrep, the company, is an application security company. And so what we're focused on is our tool, Semgrep, is actually based on research. If you've heard of OCaml, that was a tool for improving transformations in making transformations in the Linux kernel easier, just applying patches and looking for bad patterns. So the kind of static analysis we're focused on is helping developers look for really any kind of bad code. It's just that it turns out that security is maybe the most profitable kind of bad code searching. So what we do two main things for our basic analysis. One is we parse your code into an AST, an abstract syntax tree, and we take the pattern and we also parse it into and I would say the pattern is basically an abstract syntax tree querying instruction, really. I can go back to the syntax. But yeah, going back over here, the pattern is meant to, it's written to look like the code with meta variables $x to indicate oh, you look for anything here. But this is kind of saying, this is a snapshot of the AST that we want to match. And then the other kind of analysis we do is data flow analysis, taint analysis being the security application of that, which is where we look for when bad data can flow into some sink that it shouldn't be able to, that would be unsafe. And so those two things form the basic of our our open source free analysis. And then we have proprietary analysis as well, which is the interfile analysis, which again, this is also the basis of, but it makes the data flow is much more difficult there. And we also do additional things like better type resolution and naming.
Yeah, a few more questions.
Thank you very much. It was an extremely interesting presentation, and I think that the conclusion is perfect. But I have a question more about the product. I don't know Python, but I know that in OCaml, there is a lot of work that has been done in order to improve some reduced approach of static analysis for example, dealing with renaming and stuff like that. Can we imagine, for example, using from a Merlin perspective, Semgrep to perform fearless refactoring and stuff like that?
Can you repeat just the very last part of what you said?
Yeah, can we imagine that getting rid of Python and other language and just having a special interaction between OCaml IDE and tool for static analysis from Semgrep in order to have fearless refactoring?
Oh, yeah. I mean, I think there are limitations. It depends on what you're trying to express. There's always some things that you want to express that are going to be like, especially if it has more to do with the exact semantics and behavior of the code. Like, there are some things where if you could specify correctly, that would be equivalent to the halting problem. But I do think that Semgrep is a really good tool to help with adding your own personal guardrails to refactoring on top of what the compiler provides you with.
Nice. Cool. Thank you very much.
Yeah. Okay. And we have a last question.
Is it correct that for bigger customers, the Semgrep runs on their CI machines or a third-party machine?
This is also something that's changed since the time I'm talking about here. Nowadays, we have Semgrep managed scanning, which allows you just have to click a button and then on our infrastructure, we'll clone your repository, we'll scale you up to the server that you need. But at this time, we just distributed the binary that people could run. So people would run this on their own CI runners. And you might expect that customers large enough to have mono repos would be large enough to have beefed up CI runners. But in practice, it's not hard to have a big mono repo. And so we would have plenty of customers that weren't willing to do that. But they had they were still running into these problems. Another thing that's really interesting about our space is security engineers are the ones we're working for, and they're the ones who want to ensure these security checks are running. But the developers don't necessarily want that. They just want to code faster. And so, but the developers are the ones who control the configs for their CI. And so the security engineers are trying to work within the constraints of what developers have provided, and they don't have really control over that.
So my question is then, I guess this was a challenge for you when you were trying to profile that you were not running.
Yeah. This was definitely a big challenge. This is why we couldn't just hit it with the Python profiler at the moment. And what we actually did was we had our own broad profiling where we would time things and we would send that back as logs.
Thank you.
Okay. Yeah. Okay. One last question.
So it sounds like switching stuff to OCaml made everything faster and better. So is everything in Semgrep written in OCaml now? And if not, then what are the issues you've run into, porting Python to OCaml?
Yeah, so not everything in Semgrep is written in OCaml today, as much as I would like that to be true. The main difficulty is just the same difficulty you get with porting code. I think porting code from one language to another language is always difficult because it has to be backwards compatible, and the longer you wait, the more difficult it is. And I think it's hard to get resources for doing the work. So I think the most important thing there is to find the business need for why you need to port it over, whether that's developer hours saved or performance, and to be able to get the time. And there are times when I think you have to live with some compromises in the code base, even if it's not the best developer experience, because you have a more important business need.
Thank you.
Yeah, great. And thank you one more time, Emma, and one more round of applause for Emma.